listen to Daniel Vargas-Montoya from Lyon about strong Frobenius structure, rigidity, and hypergeometric.
Okay. Thank you very much for this invitation. So, this talk is about a strong Frobenius structure, rigidity, and hypergeometric equations. This presentation has two main aims. The first is to show there exists a family L of differential operators, so that for all L in L, L has a strong Frobenius structure for almost all prime number P. The second one is to study the link between the existence of a strong Frobenius structure for a prime number P and the algebraicity modulo P of the solution of the corresponding operator. So for this I am going to start for a motivation about G functions. So in this context there exists a family G of G functions, so that for all f in G there exists an infinity set S of prime numbers, so that for every P in S we have the following situation. F is a power series over Cp. I will call you that Cp is the set of rational numbers, so that P doesn't divide B. So we can reduce F modulo P. On the other hand, we have that the reduction of F modulo P is algebraic over Fpt. So in particular, there exist rational functions over Fp, so that the reduction of F modulo P is zero of this polynomial. This polynomial usually is called Frobenius polynomial. And the algebraicity degree of F modulo P is bounded by P to C. Now, examples of the G functions that verify these two properties are diagonals of rational functions. So, I will call you the definition of the diagonal of rational functions. If you take a power series in n variables over, in this case, over Q. So the diagonal of this power series is the power series in one variable, so that which coefficient is the diagonal of coefficient of this power series. And this power series is algebraic over the field of rational functions in n variables. So this result is to show, was showed by the Lin in 1984, and in this context the Lin raised the following question: if F is a diagonal of an algebraic power series, there exists a positive constant C, so that the algebraicity degree is bounded by P to C for every P in S. Note that this question is not trivial because S is an infinity set. For example, if you consider the hypergeometric series of parameters 1 over 2, 1 over 2, 1 is the diagonal of this power series, or is the diagonal of this rational function in 4 variables. So in this case, if P is a prime number different to 2, we have that F1 is a power series over Cp. So we can reduce for every prime number different to 2, and the algebraicity degree for these prime numbers is bounded by P. So in this case, C equals to 1. The Lin once answered this question when F belongs to D2, that is when F is a diagonal of power series in 2 variables, and recently Boris Adamczewski and Josenbel answered this question for any F in D. Now this situation becomes interesting because there are G functions which don't belong to D. For example, the hypergeometric series of parameters 1 over 2, 1 over 2, 2 over 3, with this symbol is the Poisson-Hammer symbol. So why this example is interesting? Because if you consider P a prime number congruent to 1 modulo 3, we have that F2 is a power series over Cp. So first of all, note that this set is infinite, but even if F2 is not in D, this situation raises the following question. Is the reduction of F modulo P algebraic over FPT? So, for answer this question, the notion of a strong Frobenius structure gives us a general point of view about the following question. If F is a G function, power series over Cp is the reduction of F modulo P algebraic over FPT. If this is the case, what could we say about its algebraicity degree? So, before giving you the definition of a strong Frobenius structure, I am going to show our motivation for using the notion of a strong Frobenius structure. Indeed, we want to study the algebraic relation between the power series FTPJ, J a natural number, over some field EP. But note that if F is the following vector, is solution of the differential system d over dt z hz, where A is a matrix over Qt, then the vector Ft Pj by definition is Pj prime. This vector is solution of the differential system here Pj dPj minus 1 A dPjc. So the idea of a strong Frobenius structure is maybe to compare this system over the field EP. So like this, we can study the algebraic relation for the series FTPJ. So now the question is, what is the field EP? So here we have the first question. What is the field EP? So the answer is the EP is the field of analytical elements. Now I am going to give you the definition of this field. For this, I am going to make an analogy between the classic situation and the periodic situation. So let A be two matrices over Qt. In the classic situation, we say that A and B are globally equivalent in Ct if there exists A in the lane Ct, so that we have this expression. This expression means that the differential module defined by A and the differential module defined by B are isomorphous as differential module. So in this case, we say that A and B are Ct equivalent. So in the periodic situation, I am going to make a similar definition, but I am going to replace the field Ct for the field EP. So we say that A and B are globally equivalent if there exists A in the EP, so that we have the same relation. So in this case, we say that A and B are EP equivalent. So I recall you that this relation means that A and B, the differential module defined by A and B, are isomorphism over the field EP. Now another interesting question is why the field we are going to compare the system over the field EP. So, but before answer this question, I am going to define the notion of a strong Frobenius structure. So I forget indeed the field EP is the field of analytic. The field EP is the computation of the CPT for the Gauss norm. So here I recall you that the Gauss norm of the rational function over C is defined like this. Is this the max of the norm of AI's over the max of the norms of BJ's. So let L a differential operator over Qt. So we can associate to L the companion matrix defined like this. Here is the matrix, is the identity matrix. Here is the column of zeros, and the last row of A is the coefficient of L. So we say that L has a strong Frobenius structure for P of period H if there exists an integer greater or equal than 1, so that we have these two matrices are EP equivalent. In the other words, there exists H in the line P, so that we have this expression. So now, after the definition, we can answer the second question. For example, if you consider the differential operator defined like this, so in this case the companion matrix is equals to 1 over 2, 1 minus t, of a solution of L is given by Ft equals to 1 over 1 minus t to 1 over 2, 1.5. And if you take A defined like this, Ft over Ft to P, P a prime number different to 2. If P is a prime number different to 2, we have that A is an element of EP but is not in CPT. So here, as you can see here, for a study for compare the system of the order 1, is necessary to introduce the field of analytic elements. And moreover, if G is another element of EP, so that we have this same relation.
Excuse me, it's a little hard to see there. If you could write. I can't see what you're writing.
Okay, I'm sorry. So, and moreover, we have that the derivation of this element is equal to AH minus HP minus 1 ATP. So this operator has a strong Frobenius structure for every prime number different to 2. The period equals to 1. And moreover, if G is another element in EP, so that the derivation, the G is equal to AG minus G D to D minus 1 A D. We have the exist C and in CP, so that G equals to C H. So, as you can see, for study the system of the order 1, we need to introduce the field of analytical elements. So now this relation is very important because this relation allows to define the Frobenius action over the solution of differential operator. More precisely, if L has a strong Frobenius structure for P of H, and H11 to H1n is the first row of H is the same matrix here. So, then for every solution F of L, we have that this expression is a solution of L. F belongs to a ring containing EP. So we fix this ring, and this application is CP linear. Then, by applying the Calvin-Hamilton theorem, we have the following result. If F is a power series over CP, solution of L, where L is endowed of a strong Frobenius structure for P of H, then the reduction of F modulo P is algebraic over FPT, and the algebraicity degree is bounded by P to n squared H, where n is the order of L. So, this term is very important because I recall you that our motivation for study the notion of a strong Frobenius structure is for answer the following questions. If F is a G function's power series over CPT, then we have the following question. Is the reduction of F modulo P algebraic over FPT? And the second question was, what could we say about its algebraicity degree? So this theorem gives us an answer for these two questions. Now, this theorem is also general because if F is a diagonal of an algebraic power series, we can apply this theorem, but we will see it later on. We can apply this theorem to the series F2, which is not in D. So, like this, we have a more general theorem for study of G functions. And for definition, H depends on P, but we will see later. But H, for a big family of examples, H doesn't depend on P. Now we have the Gauss hypergeometric equations. Indeed, these equations, but a result of the work on Saline, prove the following theorem using different methods. If A, B, C are rational numbers, so that A, B, C minus A, C minus B are not integer, the operator associated to Gauss hypergeometric equations has a strong Frobenius structure for almost prime number P, where the period is bounded for this product, where phi is the Euler-Finn function and d is the denominator function. So in this case, we see that H doesn't depend on P. Now, the work proved this theorem using its periodic homology. It's a very hard tool, but however, Saline proved is based on the classic theory of differential equations and periodic differential equations. So, extending this method, we have proved the following theorem. If L is a differential operator over Qt, and we suppose that the following conditions are verified, the singular points of L are regular, the exponents at singular points are rational numbers, the monodromy group of L is rigid, then the differential operator L has a strong Frobenius structure for almost all prime number P. So, in the proof of this theorem, the rigidity is the key concept. So I am going to recall you the definition, but first of all, I recall you the definition of the monodromy group. So let gamma i's be the singularities of L. We suppose that mi is the monodromy local matrix of L at gamma I, so that the monodromy group of L is generated by the matrices mi's with the relation their products equals to identity matrix. So the rigidity is the concept. The rigidity is important because allows to pass the local condition to a global condition. Here, the condition is given by the conjugated between matrices. So, more precisely, we say that monodromy group of L is rigid if for every ni in Gen C, so that their products equals to identity matrices, and ni conjugated to mi. Then there exists U in Gen C, so that this relation works for every I between 1 and R. So here, the local condition is given by Ni conjugated to Mi, and the global condition is given by the existence of this matrix U, because it works for every I between 1 and R. Now examples of differential operator that verify of strict condition of theorem. I will call you the conditions is the generalized hypergeometric equations. This operator is given by this definition, where delta is equals to T and T over dt. We suppose that alpha i's and beta j's are rational numbers, and the difference between alpha I and beta j is not integer. So for this operator, we have that the singularities of this operator are regular, which are 0, 1, infinity. The exponents at infinity are alpha i's. The exponents at 0 are 1 minus beta j's, and the exponents at 1 are 0, 1 to n minus 2, and minus 1 plus the sum of the difference between beta I and alpha I. And finally, the monodromy group of this operator is rigid. This result is due to leveled. So we can apply the theorem VM for this operator. But after construction of the proof, the theorem VM, we have that for this operator, if S is the set of prime numbers so that P is different to 2, and the periodic norm of alpha i's and beta j's equals to 1, this operator has a strong Frobenius structure for every P in S, and the period is bounded for this product. Here again, H doesn't depend on P. So let me write down this set S. So we suppose that S is the set of prime numbers different to 2, so that the periodic norm of alpha i's and beta j's equals to 1. So now we come back to the series F2. So I will call you that F2 is not in D, but however we can study its algebraicity modulo P. Why? Because F2 is solution of this operator. So by applying theorem 2, we have that this operator has a strong Frobenius structure for every prime number greater or equal than 5, because for these prime numbers, the periodic norm of these parameters is equals to 1. And if P is a prime numbers congruent to 1 modulo 3, we have that F2 is a power series over Cp, and for these prime numbers the period equals to 1. So we can apply the theorem 1 that implies that F2 modulo P is algebraic and the algebraicity degree is bounded by P2 squared. This 2 is the order of this operator. So for this series we have answered the question is algebraic, and we have the algebraicity degree is bounded by this constant which not depend on P. As last example, we have this power series. We have seen on Monday that this power series is globally bounded, but is not in D. But at this stage, we did not if this power series belongs to D. But however, we can study its algebraicity modulo P because F3 is solution of this operator. Then, after theorem 2, this operator has a strong Frobenius structure for every prime number greater or equal than 7. Because for this prime number, the periodic norm of these parameters is equals to 1. And for this power series, if P is a prime number different to 3, we have that F3 is a power series over Cp. So we have that F3 modulo P is algebraic, and the algebraicity degree is bounded by P3 squared cis, where this 3 is the order of this operator and cis is the period of these prime numbers. So now I am going to give you the principal ideas of the theorem Vm. For this, I will call you the theorem. We suppose that singular points of L are regular, the exponents at singular points are rational numbers, and the monomy group of L is rigid. Then L has a strong Frobenius structure for almost prime number P. So first of all, I am going to construct the set S of prime numbers which provide L of a strong Frobenius structure. For this, I am going to consider the set A defined like this. The denominator of the exponents of gamma i's, I will call you the exponents are rational numbers. The coefficient of A0t, here I suppose that A like this, differential operator. Where AIT is a polynomial over C. And finally, the algebraic numbers gamma 2 to gamma r minus 1, gamma 1 plus 1 to gamma r minus 1 plus 1, and the difference between gamma I and gamma j. So we are going to consider S like this. Is the set of prime numbers so that the periodic norm is equals to 1 for every u in A. Note that this set is finite because u is finite. Now the question is, why do we consider the set S like this? Essentially because if gamma I is different to 0, then gamma I bar different to 0 because the periodic norm equals to 1. And if gamma I is different to gamma j, then gamma I bar is different to gamma j bar, because the difference, the periodic norm of their difference equals to 1. Now I am going to construct the period H. So for this, if alpha is an exponent, so we have that P to feed the alpha congruent to 1 modulo d alpha, because P doesn't divide the denominator of alpha. D alpha is the denominator of alpha. So if you take, so like this, we have that P to feed the alpha times alpha is congruent to alpha modulo C, and I am going to take H1 equals the product over exponents. So like this, we have that P to H1 times alpha congruent to alpha modulo C for every exponent alpha. And for this, I am going to consider the theorem number generated by of gamma i's, let kappa, let k equals to the theorem number generated by gamma 1 to gamma r minus 1, and we consider H2 equals to the dimension of k over q. So like this, because the periodic norm of the coefficient of H0 is equals to 1, we have this. So finally we take H equals to H1, H2. It's important, doesn't depend on P. So now we have constructed the set S of the P and the P of H. So the idea now is to show if P belongs to S, we are going to show if P belongs to S, then A and B equals to PH minus 1 AT PA are a P equivalence. But we have a problem because the matrix B doesn't have the same singularities than A. Then it is impossible to compare locally A and B over CT. But after this expression, we have that the singularities of B modulo P are the same as the singularities of A modulo P. So by applying the theory of periodic differential equations, we have that B is a P equivalent to this matrix, where Nj is a matrix over Cp, and the eigenvalues of Nj are the exponents of L at gamma j, multiplied by P to H and the sum of the matrix Nj is a diagonal matrix over C. So, for the next, at this start of the proof, we have too many points. The first point is the following one. Let's be kappa an isomorphism between Cp and C. So we are going to consider the matrix G kappa, where Ng kappa is the matrix obtained by applying kappa of the coefficient of Nj. So like this matrix belongs to Ct. So the idea is applying the classic theory of differential equation to this matrix. And note that -1 is a apparent singularity because the monodromy local matrix is equal to identity, because this sum is a diagonal matrix over C. So we have that in this case the singularities of this matrix is a kappa of gamma j. But the set of kappa gamma j's is equal to the set of gamma j's, because I will call you that gamma j's is the zeros of the polynomial A0t, and kappa fixes the field of rational numbers. So the idea is from the construction of S and H, is to show that the local monodromy matrix of G kappa at kappa of gamma j are conjugated to the local monodromy matrix of the A at gamma j. And finally, the rigidity hypothesis implies that A and G kappa are Ct equivalent. So that by applying kappa inverse, we are going to have that A and G are EP equivalent. And finally, by transitivity, we have that A and B are EP equivalent. So I am going to calculate the monodromy group of G kappa and the monodromy group of A for the first point. So the monodromy of L. Let Mj the local monodromy matrix of L at gamma j. Since gamma j is a regular singular point of L, we have that Mj is conjugate to the exponential of this matrix, where Cj is a matrix over Q bar. And this matrix satisfies the following conditions. If lambda beta are two different eigenvalues of Cg, then lambda minus beta is not integer. And let alpha ij be an exponent of L at gamma j, then there exists an integer m, so that alpha ij plus m is an eigenvalue of Cg. But by construction, we know that P2H times alpha ij congruent to alpha ij modulo C for every P in S. Then these two matrices are conjugated. Why? Because I will call you that but the eigenvalues of Cg modulo C is equals to eigenvalues of P2H Cj modulo C. So we have that, and moreover, I will call you that eigenvalues of Nj is equals to Ph and alpha ij exponent of L at gamma j. So we have that these two matrices are conjugated, and finally we have that Mj is conjugated to the exponential of 2 I, E, B, C, D. And the other hand, we have that we are going to calculate the monoid group of G kappa. So we apply the same strategy. Let Tj be the local monoid matrix of G kappa at kappa of gamma j. Since this singularity is regular, then Tj is conjugate to this matrix where Lj verifies the similar conditions. If lambda beta are two different eigenvalues of Lj, then their difference is not integer. And if alpha is an eigenvalue of Nj kappa, then there exists an integer m so that alpha plus m is an eigenvalue of Lj. So the eigenvalues of Nj kappa are the same of the eigenvalues of Nj because the exponents are rational numbers. So for this we have that the eigenvalues of Lj are the form p to h times alpha ij plus m, where p to h alpha ij is an eigenvalue of Nj kappa. So again we have that eigenvalues of p to h cg modulo c is equals to eigenvalues of Lj modulo c. So like this we have that these two matrices are conjugated. So finally we have shown that the exponential of this matrix is conjugated to Tj. Now we have that Nj is conjugated to Tj. So we can apply the rigidity. We have showed essentially that Mj and Tj are conjugated. So the monoid group of L is rigid, then the monodromy group of L and G kappa are isomorphism. And after the Riemann-Hilbert correspondence, there is H1 in GNCT, so that we have this relation. I recall you that this relation means that the differential module defined by A and the differential module defined by G kappa are isomorphism as differential modules. So we set H1, we set H equals to H1 kappa inverse. That is, we apply kappa inverse of the coefficients of H1. So H belongs to the line CPT, but by construction CPT is contained in EP, and we have this equality. Then we have that A kappa inverse and G are EP equivalent, but A kappa inverse is equals to A because A is a matrix over Qt. So we have that A and G are EP equivalent, but we have shown that G is EP equivalent to B. Then by transitivity we have that A and B are EP equivalent. So like this we have showed the theorem VM. I stop here. Thank you.
I have a question. Do you have a theorem, you told it before, your own theorem, the first one that you showed us, about strong Frobenius rigidity?
I'm sorry, this one.
Yeah, so once you know, right, so you know L, right, and you constructed the matrix based on L, and then you're trying to find A, right, such that it satisfies the, so do you know the any restrictions on the I forgot your notations. Could you look at the slide back on A? The one which is something dt. Yeah, it's not A. About next. Yeah, on H, right? Do you know? So given A, so in your theorem, right? You said that if L satisfies certain properties, right? Then you can find H such that, you know. So the question is, do you know anything about this H? Is it going to be of special form, or like, do you like?
Yeah, but in the case where L at mum at 0 or infinity, that is where the modern local matrix in 0 is idempotent. I know the information about H, but in general, no.
So you don't know how, say, H look like?
No.
And, okay, what is then connections? Also, that's the things which you're considering obviously have some connections with Lax pairs. So what is the connection with Lax pairs? This is what I'm asking, actually. Because in Lax pairs, it's always going backwards, right? Given H, you find, you want to know how it will evolve in time, and so yeah. So the question is, how it's connected with Lax pairs? Do you know what's the connections?
No.
Well, you should have a look about Lax pairs, because you will have a shock. It's very connected. But I mean, it's not that you're repeating the work, but it's like you're looking at the problem slightly differently, from a different angle. But I mean, that's very, very.
Okay.
Any other question?
So I'll ask what is connected. And in fact, as far as I understand, the strong Frobenius structure is so to say that you have a linear differential system that is compatible with a discrete linear one, which is given by this Frobenius action.
Okay.
Lax pair point of view. So if you're starting with a Q difference equation, so the analog of this differential hypergeometric function, they does exist. You have a Q hypergeometric function. They are rigid. They have many similar properties. And is there sense or reason to look at Frobenius structure for this kind of equation? You can rephrase a similar question in the
another equations for another operators.
Yeah, you can say that. Well,
normally, the operator from the geometry has a strong Frobenius structure.
Yeah.
But the rigidity is not necessary for to have a strong Frobenius structure. But here the rigidity is essentially because it allows to have a strong Frobenius structure.
So this notion of rigidity came up in work of Fried and other people on the inverse Galois problem over Q. Somehow this same condition allows you to take a Galois group that you built as a monodromy group and then descend it down to Q eventually. In that work they have a more refined notion that some people call weak rigidity, that involves some kind of more sophisticated action of the break group on tuples coming from conjugacy classes that are fixed ahead of time. I'm wondering if you're familiar with this notion of weak rigidity, and if you think that there might be some kind of extension to the weakening of the hypothesis in that way in your results.
I don't. But the notion of the rigidity I know is the notion that I showed here, but the notion of I know there is the notion of the PAD rigidity, but I don't know. I don't.
Maybe, sorry, just to follow up on this. So, how constructive is your, you told me that you don't know much about the structure of H, but if I give you an example, would you be able to construct H, or you do you have a method, or what?
The other one?
Or that's just completely theoretical,
In the example of the order one,
No, not the order one. It's not the order one. I'm thinking about more like order 2 or 3.
Of the
So I will take your L will be order, say, 2. Because you gave example of order 1. But what if your L is...
for this operator or for
No, in your theory, the one that you just looked at. Yeah, so L can be of any order, right?
Yeah.
So if I give, so do you have, this is a theory, what I'm asking, is it constructive? So in other words, if I give you example of L, could you construct for me your H? Right, if I correctly understand, it has a strong Frobenius structure, therefore it has H such that.
No, but I given a construction in the proof, but essentially that for now the matrix H is necessary. Here we utilize using the Riemann-Hilbert correspondence, and here for now this matrix H1 is not easy.
It's not easy to determine.
But essentially, you can see that the matrix H is the matrix S1. It's given by the Riemann-Hilbert correspondence.
Okay.
But
You use it.
and
You can say
and after is the matrix H multiplied by the matrix given by the equivalence between G and B.
So let's thank you, Daniel.
Thank you.